Here we are going to see an introduction and overview to data structures and algorithms. Let us see the organization of this lecture. Introduction to data structures, classification, namely linear and nonlinear data structures, what are the operations we could do on data structures, what abstract data type is, the importance of data structures. We will see the definition for algorithm and its characteristics, the factors of an algorithm, various algorithmic approaches, and finally a summary. First, let us see introduction. In the world of computer science, understanding data structures is crucial. They are the foundation for efficient programming and problem solving. The definition for data structures is it provides us a way of organizing data. Imagine a classroom environment where we have students, they are not made to sit, and if suppose the students are all standing, it is difficult for a teacher to pinpoint a student. On the other hand, if the teacher has made the students to sit in rows and columns, then the teacher could easily pinpoint a student by saying a student from third row and second one in the third row. That is how data structures actually help in terms of problem solving. So, you know very well, computers are basically used for processing the data. Only if the data is organized in a way that is suitable for the program to fetch it, process it and produce the results, we can expect the results to be perfect, and that too in a short span of time. That is how data structures actually help us in processing, retrieving and storage of data. On the next definition is with respect to algorithms. We all know algorithm is actually a step-by-step procedure to perform a task, and that too in a finite amount of time. Our objective is to reduce the space and the time requirement for performing different steps which are part of an algorithm. So, we say an data structure is efficient only if it uses the minimum memory space and execution time. So, this slide we see the introduction and the definition for data structure. As I was mentioning before, it is a particular way of organizing data in your computer's memory so that the data can be used effectively. So, our idea is to reduce the space and the time complexities while we perform different tasks with that data. So, what you see on the slide is the different data structures, namely stack, tree, linked list, graphs and queues. So, in the following slides, we will be seeing in detail about each of these data structures. What you see here is actually a classification of data structures. As I was telling before, data structure provides us a way of organizing data in storage. So, here the first classification of data structure is primitive and non-primitive data structures. By primitive, we mean the built-in types supported maybe by a programming language. So, we call primitive data structures also as simple or single data structures. For instance, let us consider the programming language to be C. You have some built-in data types like integer, floating point, double, etc. So, all of them make up primitive data structures. The second classification is non-primitive data structure, which actually refers to data structures which are actually derived from primitive data structures. So, with primitive data structures, the speciality is any machine language instruction can straight away deal with primitive data structures. On the other hand, with non-primitive data structures, as I said, it is derived from primitive. Machine language instructions cannot deal with it straightforwardly. And again, there is a classification of non-primitive data structures into two. One is linear data structure and another one is non-linear data structure. By linear, we mean the data elements pertaining to the data structure are organized in some sequence, that is in a linear fashion. So, for when we put some 5 elements in a row, always there will be a predecessor and a successor for every element. So, organizing data in a sequential fashion is what we call as linear data structures. And nonlinear data structures, in the sense, in such case the data, instead of being organized in a sequential manner, it will be organized in a hierarchical manner. So, the best examples for nonlinear data structures are tree and graph. And again we can classify the linear data structures into two, one is static and another one is dynamic. Static, as you know, for static data structures, memory is assigned or allocated or reserved at the time of compilation. So, once memory is reserved at the time of compilation, user can no more alter its size, I mean the data structure size. For instance, array is an example for static data structure. So, in this case, when we look at arrays, when we reserve memory for an array at the time of initialization, in your program, you know the memory allocation is fixed and we cannot edit or alter the size of the array once it is defined. Say for instance, if I allocate an array A with size 5, its capacity is going to be 5 throughout after compilation. That is what we mean as static. And dynamic, as you know, here the memory size could be either increased or shrinked depending upon our requirement. And linked list is the perfect example for linear data structure which is dynamic in nature. And we have two other data structures which fall under the category of linear, which are stack and queue. And of course, when we go for implementation of stacks and queues, we can go with either static or dynamic implementation. So, this slide shows us a detailed classification of data structures where we are going to focus our attention to linear and non-linear data structures alone. So, under linear, we are going to see in further slides about arrays, stacks, queues and linked lists, and under non-linear data structure, we are going to see about graphs and trees. So, as I was mentioning before, linear data structure, you know, it is a data structure in which the data elements are organized in a sequential manner, and the best examples for linear data structure includes arrays, linked list, stacks and queues. So, I have shown here an example for each of this. First an array, then a linked list where you could see the elements are all arranged in a sequential manner. The difference of arrays from linked list is, in linked list the data elements may be at different memory locations, whereas it will all have they are all linked by pointers in between. And in case of arrays, for all the elements, memory has to be allocated in a consecutive memory locations. And then you could see stack, which is also a data structure that falls under the linear category, and two permissible operations are there with stack, one is push and pop. And with respect to queue, we could do additions and deletions, and the respective operations are NQ and DQ, which we will be seeing later on. And on then with respect to non-linear data structures, we will have a quick look into trees and graphs. So, first let us see the first example for linear data structure, namely arrays. So, arrays, the definition goes this way. It refers to consecutive memory locations. When we define an array, memory is allocated consecutively for all the elements in an array. Say for instance, if I reserve memory for 5 elements, after compilation, at the maximum I can only store 5 elements in that array, and at any point of time I may not reduce the size of the array after compilation. And arrays are of different types, like one dimensional arrays, two dimensional arrays and multi-dimensional arrays. So, in arrays, in order to access a particular element, we may be using its index, and always an array index starts from 0. So, here for convenience sake, I have shown the array index to be starting from 1 to 5, just to indicate that it has 5 elements. So, here what you see in this example is we have used an array with 5 elements, and I have shown it index and value. And likewise we can have array of any dimension depending upon our requirement. For example, if I have to store the names of students in a class, then it means every name is going to be a string, where in that case I cannot have a one dimensional array, I may have to use a two dimensional array. And in case of say matrix as an example, in that case also you may have to use two dimensional arrays. The next linear data structure is linked list. So, in a linked list, as I was mentioning before, the difference of linked list from arrays is that it imposes the elements in the list to be in some sequential order, but in actually the memory is not allocated contiguously for every node in a linked list. So, for every node memory could be allocated at different locations, but all of them are linked with the help of pointers. So, the general definition of linked list is, we will say it is a collection of nodes. So, what a node is, actually it contains some portion of data and some portion for storing the pointer or the address. The address actually pertains to the address of the next element in the list. So, if suppose we talk about singly linked list, it means the node will have space for holding one memory address. So, here what you see in this example is, we have a linked list with 4 nodes, and the first node in the list has a data value of 5, and we have a pointer named head that points to the first element in the linked list, and the other 3 elements are 7, 2 and 15. And you could see that the first node in the list, namely 5, has the address of the second node, which is 7, and the second node in the list, namely 7, has the address of the third element 2, and the last element in the list, you know, its address just contains the value of null. So, that marks the end of the singly linked list. So, the next example which you see on the right is a doubly linked list. In a doubly linked list, it is also a collection of nodes. The difference is that instead of having only one location to store the address, it will have space to hold 2 pointers, which are actually addresses to the node immediately following it and the node immediately preceding it. So, in a doubly linked list, every node will have 2 pointers, one pointing to the node that is following it and the other pointing to the node that is preceding it. In such a way, doubly linked list facilitates moving across the list in both the directions. In a single linked list, always we can navigate from the head, that is the first node in the list, and we can traverse till the last. Whereas, in the case of a doubly linked list, we have provisions to traverse in both the directions, maybe in the forward direction using the forward pointer, and in our case the next pointer, and we have the provision to go back in the list with the help of following the previous pointer. That is how doubly linked list helps in many applications. The third category is a circular linked list. So, what you see here in this example is a singly circular linked list. So, it is much equivalent to a singly linked list. The only difference is in the singly linked list, the last node address will be null, whereas in the case of a circular singly linked list, the address of the last node will be pointing to the first node in that list. So, that makes the difference of circular linked list from singly linked list. And so far we have seen 2 data structures, one is arrays and the other one is linked list. So, I told you with the help of arrays, the memory is reserved consecutively and it does not give us the flexibility to expand its size later on when there is a need. And it is where we use linked list, because it offers the programmers the flexibility to either increase the number of nodes or to shrink its size, thereby it helps in conserving the memory space. The main drawback of arrays is that there is going to be a huge wastage of space if suppose we allocate more memory for arrays and we actually use only a limited space. But in case of linked list, we actually allocate memory depending upon our requirement, and thereby linked lists become advantageous over arrays. The third data structure which falls under the category of linear data structure is stack. So, of course, stack is part of any real world examples we see. For instance, we could arrange a set of coins one over the other, and that makes us the stack of coins. We could organize plates one above the other, that could make up the stack of plates, and we could arrange balls in a can. So, that makes a stack of balls, and we usually organize books in the table one above the other, which we call it as a stack of books. The only pointer which we use in this stack data structure is the top pointer, which always points to the topmost element in that list. So, in a stack we also call the stack as a last in first out list. So, last in first out, in that sense, the data element that is added last into the stack will be the first to be taken out of the stack. So, that is why we call stack as a last in first out list. And of course, this stack could be implemented with either of the data structures which we learned before, like you can go with static implementation with arrays or dynamic implementation with linked list. But the principle of stack is whichever element that enters last will be taken out of stack first. So, there are two possible operations which we normally do with stacks. One is push and other one is pop. If I want to insert some element into the stack, then it means I am doing a pushing, and the operation is called as push. And when I take some element out of stack, then that operation is called as pop. The next data structure is queue. So, queue we may be encountering in our everyday life. Say for instance, if we go to bank and we stand before a counter, we are supposed to maintain a queue. And when we go for some reservation desk, there also we will be supposed to form a queue. So, the principle behind queue is first in first out. So, it is also a list in that sense there is going to be some sequence, right. And it is called as a first in first out list because the person who entered the queue first will leave first or gets his service done first. So, queue is also part of many real world examples, and in terms of computer science, our operating system makes use of queue for scheduling. Our printer makes use of queue for scheduling purposes. So, the whatever job we give first for printing would get printed first. So, in a queue there are two possible operations. One is called as enqueue, which is inserting into a queue, and another one is called dequeue, which means removing from the queue, removing an element from the queue. So, here for a queue to be implemented, we need to maintain two pointers. One is front and another one is rear. Front is the pointer pointing to the first element in the queue. So, you know, in a queue, the person who is standing first will get his service done first, and he will be the one who will move out of the queue first. So, deletion operation normally gets done in the front end and insertion happens at the rear end. Whoever enters the queue afresh will be added at the end. So, that is why we mean insertion happens at that end, and the name of insertion operation is enqueue. Now, we move on to some nonlinear data structures. So, nonlinear data structures means here the data elements are organized in a hierarchical fashion. So, the most popular nonlinear data structures are graphs and trees. So, let us see what a graph is. Graph is actually a collection of vertices and edges, and there are different kinds of applications which actually rely on graphs. Most of the complex algorithms usually rely on graphs. Say for instance, if I want to picturize the telecommunication network in a city, then that could be very well represented with the graph, with the help of graphs. Say for instance, if I have to map all the cities in a state and to determine the shortest distance between any pair of cities, then in that such cases also we can make use of graphs. There are plenty of algorithms that are centered around graphs, which we will be studying in later lectures. And another example for nonlinear data structures is trees. Tree is actually a collection of vertices and edges, and in a tree its origin lies at the root. So, we will designate one of the vertices or nodes to be a root node. So, we can start doing any operations on a tree from the root node, and the links that connect the different vertices in a tree, we call it as edges. There are different kinds of trees which we will be learning, like binary tree, binary search tree, AVL tree, B plus tree and red black tree. So, I will be explaining about each of these trees in the later part of this lecture. And another data structure which falls under the category of nonlinear data structure is hashing. So, hashing is actually mapping between a key and a value. So, for here in this example, what you see is we have different keys, namely apple, cola and pumpkin, and we have some hash function. So, the principle behind hashing is whenever we give a key, the key will be subjected to some hashing function, and the resultant of hashing function is called a hash. That hash will be compared for a match against the hash table, and the index that matches to the hash that is computed as a result of hash function will be the result of doing a hashing. So, in simpler terms, we can visualize hashing to be the index page on a book. So, if suppose we want to locate a particular topic in a book, instead of searching it page by page, you could very well use the index for searching. So, if you want to know the details on a specific topic, you can look for the topic in the index and then look for a match against the page number. So, the page number is the one that helps you in navigating to the respective topic. In a similar fashion, hashing is the data structure that helps much with respect to doing a search. So, it actually simplifies the search time when we make use of it for any of the real world applications. Another data structure is heap. Heap, we also call it as priority queues. There are two different types of heaps which we will be studying later. One is max heap and another one is min heap. With max heap, the root will be having the maximum value than the children, whereas in case of min heap, the root will be containing the minimum element. So, as you observe here in this example, 15 is the root of this tree heap, which is organized in the form of a tree, and since it is a max heap, you could see that all the roots have the maximum value. Say for instance, 7 is a root for 3 and 6. So, 3 and 6 are called its children. So, at any point of time in a max heap, the maximum element will be available in the root, and in case of min heap, the minimum element will be available in its root. So, let us see some of the nonlinear data structures in detail. One is with respect to trees. So, the first nonlinear data structure which we are taking into consideration is trees. So, as I was mentioning before, tree is a data structure which is actually a set of vertices and edges. The vertices can also be called as nodes. So, here in this example, you see the node in red is the root node. So, every tree will be having one node designated as root. So, we can do all operations starting from the root node in a tree. There are different kinds of trees, namely binary tree, binary search tree, and in case of binary trees, we have different classifications like binary search tree, AVL tree and red black tree. On the top left, you see an example where I have shown in a tree there will be many levels, and as I was mentioning before, one of the nodes in the tree will be designated as the root node in the tree, and the root node will always be found at level 0. And you may have any number of levels between the root node and the leaf node. In the example shown here, we have 3 levels, level 0, 1 and 2. The root node is found at level 0 and the bottommost level 2 we call it as the set of leaf nodes. So, leaf nodes mark the bottommost level in the tree, which means after that we do not have any more levels in the tree, and whatever levels you find between the level of leaf nodes and the level of root node, we call it as innermost nodes in that tree. And the example which I have shown in the right is a binary tree. Binary in that sense, every node in a tree can have a maximum of 2 branches. It may have either 0 or 1 or 2 branches. Such a tree we call it as a binary tree. So, you could see A branched into 2, namely B and C, and B again branched into 2 and C again branched into 2. And the bottommost level is the leaf level. At the leaf level we have the nodes D, E, F and G, which do not have any children. With respect to A, B and C are its children, and with respect to B, D and E are its immediate children, right. And also we have many other terminologies with respect to tree, which we will be saying in the later lectures. And at the bottom I have shown the example for a binary search tree. Binary search tree is actually a binary tree, but with a search condition. So, in a binary tree, if some condition is imposed, then it becomes a binary search tree. In a binary search tree, the condition is actually every node, that is the root node, should have a value which is greater than its left subchild, and the root node should have a value greater than its right child. So, the search condition is root node should have a value greater than its left child and lesser than the right child. So, this condition should be true for every node in the tree. If such a tree is there, then we call it as a binary search tree. And another variant of binary search tree is AVL tree, and we call such a tree as height balanced binary search tree. So, we will be studying the concept behind AVL tree later in this lecture series. And we have another category of binary search trees, which we call it as self balancing trees. So, the best example for a self balancing tree is red black tree, and of course, we will be learning about in detail in later lectures. Another nonlinear data structure which we will be using widely is graphs. As I was telling before, in a graph we define graph as the set of vertices and edges. The difference of graph from a tree is there is no designated node as root, just as we have in trees. In graphs, it is merely a collection of nodes and edges. The first example which you see on the left is a graph which includes 4 vertices, namely A, B, C and D, and you have edges or lines drawn between those vertices, which we call them as edges. And here you see all those edges are all having arrowheads, and so we call this graph as a directed graph. If suppose the graph contains edges and if all of them are directed, we call them as a directed graph. The next example you see on the right is actually a graph which pertains to different cities, and you have edges between them and they are all directed as they have arrowheads. So, it is going to be a directed graph, and you could see that some numbers appearing above the edges, which we call them as labels, and those labels or weights actually denote the distance between those two cities. So, the example which you see on the right is actually a directed weighted graph. So, as I was telling before, graphs are usually used for many of the complex algorithms, which we will be seeing in later part of this lecture. So, consider an example like this, a contact list in a phone. Now, having seen various nonlinear and linear data structures, let us see how we can implement this contact list in a phone. We have plenty of options. I have shown here as an example 2 such examples, one with array of structures and another one with a hash table. Let us see the first example. You know, in a contact list we normally preserve the name of the contact which could be your colleague, friend or any family member. We may be storing their name, and in addition you may even store their email IDs, right. So, in this case I may require 3 fields, one to store the name, another one to store the contact number, and a third one to store the email. So, if suppose I make use of structure for every contact in my contact list, I will have 3, I may have to store 3 fields. So, thereby I will be using I will be defining a structure with 3 members, one for name, another one for phone number, and another one for email ID. So, here in this example you could organize contact list in the form of an array of structures. You know, if it is an array, then we may have to allocate memory in consecutive manner, right. So, all the contact numbers in this contact list will be arranged one after the other, that is what you see. So, here when we talk of its advantage, its implementation is going to be very simple, but search time may be more, just because if suppose this list is not sorted, then in order to locate a particular contact from this contact list, I may have to traverse this contact list from the beginning till the end, and that may take more time if the number of contacts you have in your contact list is huge. On the other hand, the same contact list can be implemented with the help of a hash table, which we discussed before. So, you know, hash table is just a storage. We have index and the associated values. So, given a key, here key is going to be the name of the person which you want to retrieve from your contact list. So, you subject the key to the hash function, and hash function will give you a match to the respective index in your storage. Thereby it simplifies the search time when we look at contacts from your contact list. In real world examples, in our phone we are using actually a variant of this hashing data structure. So, to conclude, we have seen so far an introduction to data structures. So, as I was telling before, in the introduction I told you data structure is a way of organizing data in memory. The purpose of learning data structures is, we know in computers we store data, and later on we may have to retrieve data in an efficient manner, and that is how data structures help. And algorithms is as such, it is a step by step way of solving a problem, and that too in a finite amount of time. And together data structure along with algorithms make problem solving easier, and we learnt the classification of data structures like primitive and non-primitive, and under non-primitive data structures we learnt what linear data structures is. Linear in the sense the elements, data elements are all arranged in a sequential manner, we call it as linear. If the data elements are all organized in a hierarchical manner, then we call it as non-linear data structures. And then we saw some examples for linear, namely array, linked list, stack and queue, and we studied some examples for non-linear data structures, namely graphs and queues. And we saw one real world example of how to implement a contact list using any of these data structures which we learned before. So, in the forthcoming lectures we will be seeing the various operations and what algorithms are, and its factors and characteristics, its various algorithmic approaches. Thank you.